Yes, now we are
Yes.
live.
So welcome everybody to this evening of Learning Physics with Conceptual and Problem-Based Approach, organized by the National Academy of Sciences, India, NASI, Delhi chapter. We are also live on YouTube presently, and we have with us today as a speaker for solid state physics, Dr. P. Senthil Kumar from the Department of Physics and Astrophysics. And we shall have another talk at 7 p.m. by Professor Anirban Kundu from University of Calcutta for atomic physics. May I have the next slide, please? Yes. So it's a pleasure for me to introduce Dr. P. Senthil Kumar to the audience and the attendees. Dr. P. Senthil Kumar completed his PhD degree from the Central University of Hyderabad in the year 2008 in the field of experimental condensed matter physics. And after several postdoctoral research works, he joined the Department of Physics and Astrophysics in the year 2008 and continues till date. He has 15 years of research and teaching experience and has taught courses such as quantum mechanics, advanced solid state theory, laser and spectroscopy, etc. He has started the experimental plasmonics group, and 5 PhD students have graduated from the group. He has more than 50 research publications in international journals and is one of the most cited researchers in the field of plasmonics. His name has been included in Marcus Who's Who in the World in 2014, 31st edition. Welcome, Dr. Senthil. It's a pleasure to have you again here with us with detailed solid state physics knowledge. Welcome, sir.
Thank you.
We also, yeah, yes, please. We also have the pleasure of having with us Professor Ajay Kumar Khattak. He is the chairman of National Academy of Sciences India Delhi chapter, and it is only under his guidance and chairmanship that we are able to conduct these programs for the benefit of the students. Welcome, sir.
Thank you. Good to be with you. I am sorry I cannot usually show up. This is life has been, but I wanted to listen to Senthil Kumar. And I look forward.
Thank you, sir. It's a thank you.
What are you going to speak on? Solid state theory?
No, today I'm planning to speak on Hall effect.
Oh, very good.
Okay. So, good evening, everyone. Okay, so today let me share my screen. Where is that? Okay, just for a recap, yesterday we have seen the root theory of metals and dielectric constant, plasma frequency, right? So is there any queries from the students? I would be happy to answer. Otherwise, we can proceed further. Okay. Are there any queries on yesterday's topic?
So students, if you have any queries, please write them quickly into the chat box. So there doesn't seem
so today we will,
yeah, please continue, sir. Please.
Yes. So today we will start a new topic, Hall effect. Okay. So let me share my screen. Okay. So we will see how Hall effect, what is Hall effect, what is its effect on metals and semiconductors, and the very basics of Hall effect. Okay. So, okay, till now we have seen this root theory of metals. Okay, as okay, this just a summary of whatever we have seen till now. Like this independent electron model, and it considers electrons as free electron gas, right? And they are freely moving in the background of ionic core, positive ionic core, right? all these things, there are core electrons remain bound to the nucleus, and valence electrons wander free away from their parent atoms. That's why they are called conduction electrons or free electrons, right? So this is a summary of whatever we have seen till now. Now, we are going to see how this theory, whether it works well for the so-called Hall effect or not. Okay, that's what we are going to see. And so before going into Hall effect, okay, this Lorentz force, all of you might remember, okay, the right hand thumb rule, right, which you have studied right from high school days in basic physics, right? The force acting on a charged particle is the electromagnetic field is like QE into QE with respect to electric field and magnetic field B cross B, right? So this Lorentz force. So whenever there is a interaction with
Your
electromagnetic.
slides are not changing. Your slides are not changing. We still have the slide on plasma frequency.
Is it so? Is it changing now? No. Can you see the screen? No?
Dr. Senthil?
Yes.
Dr.
Yes.
Senthil, we are seeing the plasma frequency slide. So if
Okay,
it is the same PPT, then you have to check it. And if it is a different PPT, then it should be open onto your screen. Stop sharing this one and start sharing that one.
Yeah. Okay.
Is it a different PPT?
Yes. Because I opened it before, so that I think that one you are seeing. Okay.
Yeah. So you have to stop sharing this one and share again.
Yeah. Just,
Share again the one that you would like to use.
Yes. Sorry for the.
You may have to repeat the.
Yeah. Sure. This one. Okay. So,
Yeah, that's correct.
yes. Now is it visible? The screen,
Yes, Lorentz force.
right?
Yeah.
Screen.
Yes, sir, the
Yeah.
Lorentz force.
Yeah. So this is visible, right? The screen is visible.
Yes, sir.
Yes, sir. It's written reminder the Lorentz force.
Yeah. Okay.
Okay, sir.
So this is just to remind you the recap of all the basic forces acting on different this one. Okay, just learn based on Lorentz force. Now we'll actually go into the what is Hall effect. Okay, so this is nowadays this is a very basic physics lab experiment, solid state physics lab experiment, right? I think almost in all universities or colleges. This experiment is available in BSc or even MSc labs, right? So hope all of you are familiar, but we will start anyway from the basics, right? So you have a sample which is a flat sample with some thickness, which is basically in general they take a semiconductor sample, right? Silicon or germanium in the lab, right? So you pass electric field along the x direction, like along this direction, right? So the electric field along this x direction, and you pass a perpendicular magnetic field, right? So the magnetic field is shown perpendicular to the plane of the sample, right? And so what happens with application of both electric field as well as magnetic field in the given sample, right? And where is the Hall effect, Hall voltage or Hall effect occurs in the sample, That's what in the basic experiment you do how to measure the Hall voltage, and by measuring Hall voltage, what is the charge carriers in the given sample. That's what you will find, right? So this is this experiment has a lot of physical insights into. Okay, the main advantage of this experiment is to find the nature of the charge carriers, right? Whether the charge carriers are responsible for the Hall mechanism, which kind of charge carriers, and how they are influenced by the basic electric fields and magnetic fields, right? So this basic experiment gives a lot of information, physical information about the sample and its nature, right? So, but you have to remember that this Hall effect was discovered in 1879, right? So where at that time, not even physics about electrons were not known, right? So this Edwin Hall is very, very, uh, uh, very intuitively thought of this experiment. Okay, so his, I think the students should read about his autobiography. So that's there are very interesting incidents are written in his book, autobiography book, right? I think you should read that, how he got inspired to do this experiment. Okay, he was inspired to do this experiment by listening to Maxwell's lectures. Okay, Maxwell's papers. Maxwell, the person who coincides the Maxwell's equations, right? The four electromagnetic equations are, by listening to his papers or reading his papers, he got inspired. What is a charge conductor? How the charge or electric current is affected by the magnetic field.
149. Enjoy a safe delivery with Zomato. Order now.
Hello.
Please self-mute yourself.
Yeah, is it from my side or?
No, sir. I think somebody has put on their speaker.
Okay. So that's why his autobiography is a very, very interesting one. So it's available even in Wikipedia. You can read about that. Okay, very, very. Sorry, I lost my screen.
Yes, sir. There is some problem. Let me check.
Should I share it again?
1 minute. Yes, I think something flashed in between.
Yeah, Harshit has shared his screen. Who is Harshit?
Harshit, why have you shared your screen? Are you a new attendee? Nobody, I request all the attendees, no sharing of the screen. Don't touch the bottom of your screen. Keep yourself on mute and your video off. If you do not continue to listen, then we'll have to remove you. So please be careful. Don't share your screen. Don't touch the bottom of the screen. You don't require it. Just keep watching and keep your hands away from the main screen. If you touch share screen, then the video and the audio will be disrupted. Yes, sir. Please continue. I think it was by mistake because on phone, you touch somewhere and actually the lower buttons get pressed.
Yeah,
so maybe somebody, sorry. Yeah. Please continue.
Yeah. So I request the students to just in your free time, just read about his Edwin Hall's biography, as well as even Maxwell's biography. They are very, very interesting things, how they have done at those time, 1879, okay? Even Maxwell did it before 1870s, okay? So they are very, very, they have a huge intuition, okay, to perform this experiment. Even though he performed this experiment in 1879, a lot has been, nothing has happened for over almost 100 years. After 100 years only, how much effective this Hall effect, okay, we came to know. So, but he has done it just 100 years before itself, okay, before everyone else does. So that is the beauty of this experiment, okay. So every time you do this experiment, you will get at least some basic, very new basic understanding about your given sample, whether it is a semiconductor or a metal or whatever sample it is, right? So let us go step by step. What is this experiment about, and how to perform, and what are the informations you can actually obtain from this very basic experiment, okay. So okay, this is a basic experimental setup. You need a thin or yes, lighter thickness sample, okay? Preferably a semiconductor sample. And okay, you need a electric field to pass through the length of the sample, and a perpendicular magnetic field, so that you measure over the across the thickness the Hall voltage, okay. That's what simple. The experiment as such is simple, but to arrive at this one, Edwin Hall has done many trial experiments of different ways, and mostly he was failed, but ultimately he could get this the so-called Hall effect, okay. That's what we are going to see how it works, okay. Okay, so okay, this is another setup of the same Hall effect measurements. Like here, you can see clearly how where the current passes through the length of the sample, and the magnetic field, perpendicular magnetic field. Okay, and where is Hall voltage, Hall resistance is measured, right? Or XY over the in the XY plane, you measure the resistance and what happens. Okay. So that's where, so when you apply both the electric and magnetic field, what is the Lorentz force acting on the charged particles or free electrons in the sample, or conduct free electrons in the sample? What happens to them when they simultaneously be subjected to both the electric field and as well as magnetic field, but in perpendicular directions? The electric field is along the length of the sample, and magnetic field is as shown here, perpendicular to the sample, right? Because as you know, in an electromagnetic wave, the electric field component and magnetic field component are both perpendicular to the direction of propagation of the electromagnetic wave, right? So both electric field and magnetic field are perpendicular to each other, okay? So that's why the electric field is applied along the length of the sample, and magnetic field is applied perpendicular to the sample, okay? So what happened? What is the effect of electric field? So okay, first let us pass electric field along the length of the sample. So when you pass electric field, what happens in the sample? Say, assume that it's a semiconductor sample, okay? Say silicon or germanium, for example. So when you apply electric field along the length of the sample, so what happens in the sample? When you apply an electric field to a semiconductor, a charge separation, a potential difference is created, right? The electrons move opposite to the electric field, direction of the electric field. If the direction of the electric field is from minus x to plus x, the electrons goes opposite in the direction, right? Opposite direction towards minus x, right? So there is a charge separation of electrons on one side, and the positive charge, the ionic cores on the other side happens, right? So when you apply an electric field, the charge separation happens. Now, simultaneously you apply perpendicular magnetic field, okay? When you apply a perpendicular magnetic field, what happens? Okay? As per Lorentz force, the charges, the electrons get affected by the magnetic field, right? They get deflected by the magnetic field, perpendicular field, right? That's what is the Lorentz force equation, V cross B tells us, right? So when you apply a magnetic field, the already now, because of the electric field, the electrons and the positive charges are separated. Charge of potential difference is created. Now you are applying a magnetic field perpendicular, right? So what happens? The electrons which are moving at a faster rate, they get deflected by the magnetic field. So again, so there is a charge separation perpendicular to the charge separation of the due to the electric field happens. Okay, the charge separation happens in the perpendicular direction due to the electric field, right? So does it mean that all the electrons, all the charge carriers get affected? No. How much charge carriers gets affected, right? So that's not all the charge carriers gets affected. Only on the surface of the sample, right? On the surface, only those electrons which are moving with free electrons in general, right? They are only get affected by the magnetic field at a faster rate, whereas the bound electrons, which are bound to the nuclei, right, or you can call them as core electrons, right? Those core bound electrons are not affected, deviated too much by the magnetic field, right? So only the surface charges gets affected more by the magnetic field. So there is, so because of the electric field, there's a charge separation along the length of the sample, but because also because of the magnetic field, there is a charge deflection, right? The magnetic field due to Lorentz force, the charge deflection happens, and because of that also there is a opposite charge which potential difference created along
There are
perpendicular.
questions in the chat box. Hello.
Yes,
So
yes,
would you like to take
yes,
questions in between or at the end?
yes, yes, yes. No, anytime. So if they have any queries, they can ask immediately. Okay, what are the
So
questions?
there is one question: holes in the semiconductor having positive charges.
Yes.
If I consider these holes as positrons,
Okay.
so holes are considered as the particles or not?
So what? Okay. So what is what now? Okay, it goes to entirely different. What? How do you define a positron? Okay. Or how do you define a hole and how do you define a positron? Okay. So what is a hole? If you say, what is a hole? Okay. Suppose in a semiconductor. Okay. Take a semiconductor. If you apply some potential, right? What happens is the electrons from valence band goes to the conduction band, right? With if you apply energy which is higher than the band gap of the given semiconductor, the electrons from the valence band goes to the conduction band. So which means the electron whichever is going to conduction band from valence band creates a hole in the valence band, right? So that is the, so whenever an electron is removed from the original lattice site, okay, it creates a hole in the lattice site. So that is a definition of a hole, right? Now, what is the definition of a positron when you say, right? So, okay, there are different definitions for positron. So it depends on how you take the positron. So does it, okay, if you consider positron and hole are the same, okay, but are they same? No. Okay, positron and holes are different entities, okay? So the hole is just a empty space created by the electron, okay, removal of electron from its lattice site, okay? So that is what is considered as hole. But positron is a different, this one which, okay, we are not talking about it here, okay? So the definition of positron and hole is entirely different, okay? So the positive charges here, okay, whatever is given here refers to holes, okay? Because the holes are created by the removal of an electron from a particular lattice site, okay? So that is what is defined here, okay? We are not talking about positrons here, okay? So is there any other question?
No, sir. No other question.
Okay, so shall I continue?
Yes, sir.
Okay, so we are considering only here the holes, okay? the positron, the definition of positron is slightly more okay, technical. In when you can consider a positron as a whole, okay, so that is okay, again more involved, which we are not concentrating here. We are just to the very basic because okay, as you can see, the Hall effect was discovered in 1879. Okay, at that time, not even the concept of hole was clear, right? Or electron was clear. So there was no question of positrons at that time. Okay, so now, there are two potential difference or charge separation happens because of the electric field as well as because of the magnetic field, applied magnetic field. Okay, so now when you measure, is it is the charge potential difference or the charge separation keeps on increasing if increase the electric field or the magnetic field. Ideally speaking, yes, in this case, it should keep on increasing when you increase the electric field or magnetic field. But actually in the experiment, okay, it does not happen like that. Okay, so after a certain value of the electric field and the magnetic field, the charge separation saturates. Okay, so that is what was bustling at that time. Means people could even Drude or Lorentz or Hall could not understand why it has to saturate. Okay, so that is okay. That's what leads to more advanced phenomena, which we'll see in the course of time. But right now, so what happens when you apply more and more electric field and magnetic field to the given sample? Okay, so that's what you know. So okay, this is a basic experimental setup which Hall has used in 1879. So you pass current along the length of the sample, right, and perpendicular magnetic field, and you measure the Hall voltage along the thickness of the sample. Okay, so over the thickness, if you measure the Hall voltage, there is a charge separation which happens, which is our potential difference is created, which are not affected by either by the magnetic field or by the electric field. Okay, so the Hall voltage is given by the charge carriers, okay, which are not influenced by either by the applied magnetic field or the applied electric field. Okay, so they are they behave as if they are not influenced by either the magnetic field or the applied magnetic field or the applied electric field. Okay, they are free from effect of both of these one. So that's why when you measure Hall voltage, okay, what happens? So this is what according to Drude theory, it should not change. It should be constant for any applied magnetic field. Okay, but actually when you measure, this is what you measure in your lab experiment, right? As a function of magnetic field, it linearly increases. Okay, so this is what Drude theory could not explain. Okay, because of its independent electron approximations. Okay, but whereas this is this one is an experimental one. Okay, this one is as predicted by Drude theory. Okay, so after almost 20 years or 20 years of after the Hall experiment, Drude tried to explain, okay, using his theory, Drude theory, but he found out that as you increase the magnetic field, the Hall voltage should be a constant. Okay, but actual experiment, you see this one. Okay, it linearly increases. Okay, so that is what Drude theory could not explain. So even people were worried about why it is happening. Okay, they could not find a proper theory at that time. Okay, so this is okay overall summary of what actually the Hall effect gives you. Okay, because of the electric field as well as the magnetic field, Lorentz force acts on the charge carriers, right? You get when you apply a electric field along this length of the sample, okay, the transverse current density is 0. Okay, the charge separation happens only along the length of this one. So
Sir, one more question is there.
Yes, yes.
Student is asking, in Hall effect we use square or rectangular shape material, but if we use cylindrical and spherical material, will that be valid?
Yes. Okay. As a lab experiment, okay, it is very easy to measure in spheric means square or rectangular samples. Okay. Nevertheless, you can do in this one cylindrical samples, but the perpendicular direction you cannot measure in a cylindrical sample. So it's a technical issue, like experimental setup issue. Okay, but nevertheless you can try. Okay, as this one, but the to see the effect in the perpendicular direction, it is very difficult to view in a like cylindrical sample. That's why in general the other shape like cylindrical or other shape materials are not used in the lab experiment. But nevertheless you can try, but the problem is already in the perpendicular Hall voltage is very weak. Okay, as you can measure even in the over the thickness of the sample. Suppose okay, you can ask the same question, why the thickness of the sample should be it's a very thin sample. You use in normal lab experiment, if you see, you use a very flat, almost flat or very thin sample. Okay, so why not a bigger, thicker sample? Okay, so whether you use a thin sample or a thin square or rectangular sample or a thick square or rectangular sample, right? What will be the difference? There will be actually no difference. Okay, whether you take a thicker sample or a thinner sample, it doesn't matter, because whatever electric field or magnetic field you are applying, it's going to affect only the surface or free electrons on the surface. Okay, so the bound electrons which are attached to the, if it's a very thick sample, only on the surface, whatever electrons or the charge carriers, they are going to only get affected by the applied your both electric field as well as magnetic field. Okay, the whatever samples on the inner surface of the or deep inside the surface of a sample is not going to be deflected by the applied magnetic field or the electric field. Okay, so it doesn't matter whether you use a thick sample or a thin sample. Okay, so that's why in any experimental setup, lab setup, you will see because you will see a very thin or almost flat sample. Okay, and again the y square or rectangular sample, because it's okay easy to see the okay direction, perpendicular direction. Suppose if we use a cylindrical sample, okay, so then identifying as a lab experiment, the students will be very difficult to identify okay which direction the electric field is flowing and which direction in the magnetic field is flowing, and perpendicular to that direction where you have to exactly measure the Hall voltage. That will be a experimental technical problem, not a Hall effect problem, but it's a technical experimental problem. Okay, experimental apparatus problem. So to make things easier, okay, you use a square or rectangular sample, but it doesn't matter whether you use a thick sample or a thin sample. So thin, even if it is a thick sample, it's not going to. It's only the surface charge that's going to involve. So that's why normally in any lab experiment you use a thin sample. Okay, so the technical problem of using cylindrical this one is this one, okay, to identify the perpendicular direction of different, like in a square or a rectangular sample, it's easy to identify. Okay, nevertheless, you can try, but since it's the Hall voltage is very weak or very small, okay, as you can see in Hall voltage, what is the range of Hall voltage in your experiment? Okay, if you have done the Hall effect measure experiment, what is the Hall voltage range of Hall voltage you measure in the experiment? Any idea what is the range of the Hall voltage? Okay? Whether it is in volts or millivolts, microvolts, nanovolts. Okay? So the Hall voltage will be of the range very weak. It should be very weak. It cannot be in volts for sure, definitely, right? So it should be in the microvolt range. Okay, so even if you take a thicker sample, then all the more it will be reduced. Okay, there is a the surface is the same. Okay, so the bound electrons are not going to participate in the Hall effect measurements. Okay, only the surface electrons are going to participate. So it doesn't matter whether you take a thick sample or a thin sample. Okay, but only thing is you have to identify the directions of the electric field as well as magnetic field in a proper manner, so that perpendicular to both the electric field and as well as the magnetic field, you can measure the Hall voltage. Okay. Otherwise, if you cannot identify the different perpendicular direction, like in a cylindrical sample, then what you measure may not be a Hall voltage. Okay, it will be the direct voltage from the either from the electric field or from the magnetic field. Then they will not. So the simple test is to see whether, as a function of magnetic field, the Hall voltage is linear or not. Okay, so if you are measuring in not in a perpendicular direction to both the applied electric field or magnetic field, then you will not get the Hall voltage as a function of magnetic field, a linear curve. Okay, so that itself shows that what you are measuring may not be the Hall voltage. Okay, so that's why simple square or a rectangular sample would be best to identify correctly the directions of the electric field and magnetic field as far as a lab experiment is concerned. Okay.
Yeah.
Yes.
Hmm?
Is there?
अच्छा बारिश होती है और है
Nothing. Diksha, please mute yourself.
Okay. Okay. So this is these are the parameters which you can measure, like Hall voltage, okay, and Hall resistivity. You can measure with respect to the area of the sample, length and the area of the sample, and even the Hall coefficient, right? RH, okay, which you can measure by different directions of the applied electric field as well as the current density, right? So the RH gives you the Hall voltage or Hall resistance, which gives you the sign of the charge carriers, right? Right, in a given semiconductor, like suppose if it is a P-type semiconductor or a N-type semiconductor, which one? So if it is an unknown semiconductor given to you and you want to know whether it is a P-type semiconductor or a N-type semiconductor, right? The best way to, or best direct way to measure it is Hall effect measurement. You do the Hall effect measurement of an unknown sample, it will directly give you the sign of the charge carriers. So from that you can know, okay, my given sample is whether N-type or a P-type semiconductor, right? So this is I think, as far as I know, this is the only experiment which directly gives you the sign of charge carriers. Okay, there are other, like even conductivity measurements, AC or DC conductivity measurements. Okay, that will give you only the effect of the charge carriers. But here, this actually directly gives you the sign of the charge carriers. That is a major advantage of this experiment. You don't have to. So if you are given an unknown sample, you just do the Hall effect and measure the Hall voltage and Hall coefficient. It will directly give you the sign of the charge carriers. Okay, so that much effective this experiment is. Then so till date, this is the only experiment, only standard experiment. Okay, for measuring the sign of the charge carriers. Okay, so this you always the student always keep it in mind that the only experiment which gives you the sign of the charge carriers, like RH is positive for positive, like p-type semiconductors, and negative for negative or n-type semiconductors, right? So this experiment directly gives you that. Okay, so and okay, the other quantities of interest is that, okay, that we will see in the next class, that magnetoresistance. Okay, what is a resistance? Okay, which is you can call it as Hall resistance or even magnetoresistance. Okay, so again, this magnetoresistance is another important aspect. Okay, that is derived from this Hall effect measurement, right? And which has this magnetoresistance, which has a lot of applications, right? As you know, all your magnetic drives, like hard disks, right? Hard disk, USB storages, right? Everything, all storage, means digital storage devices use this principle of magnetoresistance. Okay, this we will see in the next lecture. Okay, so that is again one of the outcome of this Hall effect measurement. Okay, even though Hall measured means predict means measured actually this magnetoresistance, there was no proper theory again. So this also came after 100 years of Hall effect. People came to know about the importance of this magnetoresistance. Okay, and ultimately it got a Nobel Prize. Okay, so that's again a different story. But a person who actually started in 1879, unfortunately, he didn't get a Nobel Prize. Okay, maybe he's beyond like people like Hall and Maxwell, right? Didn't get Nobel Prize, but that doesn't. They are maybe they are beyond Nobel Prize. Okay, at that time, 1879. Okay, there was no Nobel Prize. So, but nevertheless, people have appreciated even at that time his work, this work, even though this work has no significance at that time, 1879. But people has given good scientific importance for his for Hall's work. Okay, and okay, this is his PhD work, doctoral thesis work, and based on this work, he was awarded a doctoral degree, right? So that is okay. That's everything is written clearly in in his autobiography. So you should read that. Okay, I was reading it, and I was very much fascinated with this Edwin Hall. Okay, so based on this one, okay, there were 3 Nobel Prizes. Okay, like one is for magnetoresistance, and 2 others for integral quantum Hall effect and fractional quantum Hall effect, right? So, but the basic of those, the Hall effect, actually, right, didn't get the Nobel Prize. Yeah, so this is one of the intriguing things about science, right? Research in science. So okay, so these are the major so even though it's a very simple experiment, like you pass current along the length of the sample, electric field along the length of the sample, and perpendicular magnetic field, and measure. Okay, what students do is just apply electric field and apply a magnetic field perpendicular and just mechanically measure voltage perpendicular to both electric and magnetic fields, right? But you can actually derive this much information if you actually instead of that doing that has become now a routine experiment. I think even in high schools they have this experiment, I suppose. Okay, but now what could be done in even in like undergraduate or in postgraduate labs is all this the other measurements like Hall resistivity along different directions, right? Like along the length of the sample as well as breadth of the sample, right? Or along the thickness, what happens? Okay, because thickness it is a constant one. Thickness it will not change, but along the length and breadth of the sample, which is what is this rho yx and normal resistivity and Hall resistivity, right? That changes very drastically, okay, depending on the applied electric field as well as magnetic field. So that should be more sensible for the students, at least in undergraduate labs, to measure them, right? Instead of just routinely measuring Hall voltage perpendicular to the direction of both electric field as well as magnetic field. The Hall resistivity, they should be able to calculate or measure it actually, right? So that should be the way it should be. This experiment should be seen in a more rigorous manner. Okay. Okay. Now we will just see how what are the parameters you can get, right? Or what are the basic theory. Okay. This again, we are using root theory now, right? Even though it does not explain why Hall voltage has to increase linearly with one. Rest of the things it can orally means analytically explain the Hall effect to the maximum possible extent. Okay, so initially the velocity of the charge carriers along three different directions are given by this one, like Vx, Vy, Vz, and the electric field is along the x-axis, right? And magnetic field is along the z-axis. Okay, that's conventionally electric field along the x-axis, and z-axis is magnetic field, right? So the force, Lorentz force acting on the given charge carriers are given by this equation. And as you can see, this equation we have seen in the root theory, right? So the force acting on when these charge carriers are acted upon by an external electric field. Okay, this is what is the force which we have seen during the root theory. This one, right? So this is now equivalent to the Lorentz force, right? Lorentz force acted upon the charge particle, both E for the electric field and V cross B for the magnetic field, right? So now, so we see the force along different directions, right? Along the x direction, what is the force acting on the charge carriers? Okay, so that is what is given by this simple from the Lorentz equation, right? Force along the x-axis or x direction, and force along the y direction. Okay, it's perpendicular direction. There is no effect of electric field, so only the magnetic field component is there. Whereas along the x-axis, both the electric field, x component of the electric field, as well as the magnetic field components are there. Okay, so these two are the simple force acting along different directions, x and y directions in the given sample, right? When you apply both electric field as well as magnetic field simultaneously. Okay, so the steady state conditions. Okay, under steady state conditions, what happens? Okay, you can equate these two equations along different directions, force along different directions, x and y directions, and equate them and try to find okay, what is the possible solutions, right? So these are the two equations you will get. Okay, and from this we can find what is this one, omega c, right? Which is as you know, the cyclotron frequency, right? this is EB by M is called the cyclotron frequency. So you substitute those things in this equation, right? Equation of motions, right? And try to find solutions, right? For EX and EY. So that's what you will get. EY, you will get like this one by simply solving this root theory equation for equations of motion, right? You will straight away get with respect to say the applied magnetic field as well as tau, the relaxation time, right? Which we have seen in root theory, right? So you can get the electric field in terms of the magnetic field components, okay? So, and that's how the Hall coefficient is defined by this formula, okay, and which gives you the directly the charge carriers minus 1 by n. So this is for if it is negative, the Hall coefficient is negative. We know that it is for charge carriers are negative or n-type semiconductor, right? In an n-type semiconductor, when you measure the Hall coefficient, it will be negative. So those are we can find, we know that, okay, this sample, given sample is a n-type semiconductor, which is having negative charge carriers, okay? So that is what this Hall coefficient gives definition, okay? And yeah, so now at that time in 1879, people want to know, okay, there are some charge carriers which are not deflected by both by the applied electric field as well as magnetic field. So that's why they are they create a charge potential difference perpendicular to them. So what is the importance of that? Okay, so that's what people even at that time were thinking, but they could not, of course, they could not get a correct answer for that. But nevertheless, they were actually trying to find. So one thing they could find is that, okay, it can determine the type of charge carriers and their again carrier density. Okay, how much is the charge carriers involved in that actual actual potential difference and the perpendicular direction. Okay, with respect to both the electric field, applied electric field, and the magnetic field. Okay, that they were clear. Okay, that will give you the carrier density and the carrier type, whether it is positive charge carriers involved in the process or negative charge carriers. Okay, so that, but how? Experimentally, they could see that, but behind that, okay? That's what is lacking at that time. Okay, so even Hall himself was trying to understand the whole phenomena. Okay, by doing different possible measurements. Okay, but nevertheless, okay, he could not proceed further of more than finding the carrier type and the carrier density, right? So
Sir, there is one question.
yes, yes.
Sejal is asking, why don't we use metals to observe Hall effect?
Okay. Okay, I thought, okay, we will come to that, but anyway, okay, since it has been asked, so in a semiconductor, okay, so in a semiconductor, okay, since there is the charge carriers are sitting in the valence band, and there is some energy needed for the charge carriers to come to the conduction band, right? So that you can work on with say some range of electric fields and magnetic fields, right? But whereas in metal, as we have seen in root theory already, that there are free electrons, okay, which are of the concentrations of which are of the order of Avogadro number, right, in a given metal. So once you apply a electric field, all the charge carrier, all the free electrons, right, will be moving in one direction, right? So the scattering, this one will be more in metals, okay? The scattering of different electrons, right? Free electrons, okay, is more in metals, right? When you apply an electric field as well as perpendicular magnetic field. So in metals, all the more in hello.
हमको ही जाना पड़ेगा। लेकिन कहाँ यार 8 मिनट पहले कहाँ थे भाई?
In already in semiconductors, as we have seen, the Hall voltage is very weak. Okay, so all the more it will be much more weaker in metals. Okay, in principle, yes, you can do, but the effect will be very weak in the metals. Okay, because there are a lot of scattering due to the free electron. Number of free electrons is very high in metals. Okay, so the Hall effect will be very weak, but nevertheless, it will be it is there wherever there are free electrons, right, which are affected by the electric field as well as the magnetic field. Definitely, the Hall effect is there. Effect of magnetic field and electric field is there, but that effect will be minimal in the case of metals. Okay, already at room, if you are doing at room temperature, right, there are a lot of thermal fluctuations. Okay, so you don't know whether actually the Hall voltage, right, is due to the actual applied electric field and the magnetic field, or the thermal fluctuation, mere thermal fluctuations. Okay, so that's why it's very, nevertheless, if you go, okay, if you have a sophisticated low temperature measurements, low temperature setup and things like that, yes, you can measure it for metals, okay? But in a normal UG or master's lab, as a lab experiment, it is very difficult to use metals. So that's why normally semiconductors are used, okay, which has, even though weak Hall voltage, but nevertheless you can measure it appreciably with minimal setup, experimental setup, even at room temperatures. Okay, that is a key. So if in metals, if you want to measure, yes, you have to go to very low temperatures, so that you are sure that the thermal fluctuations are removed, okay, completely. Okay, and again for that you have to go to very low temperatures. Okay? That's why, okay, we will see later in this one, like integral quantum Hall effects, right? Whether it's integral or fractional quantum Hall effects are not possible at room temperature because the thermal fluctuations dominates. Okay, so you have to go to low temperature, very low temperatures, in fact. Okay, for seeing quantum Hall effect. Okay, that's what we will see towards the end of this this one. So thermal fluctuations is the key in the metal, in the case of metals. So you cannot differentiate at least by room temperature measurements, you cannot differentiate between thermal fluctuations and the actual effect of magnetic field and the electric field applied to the given sample. Okay, so that's why as a lab experiment, you will not use semiconductor, you will not use metals to measure Hall voltage or Hall effect. Okay, so that is a key part. So as a normal in the lab experiment, you generally use semiconductor. So that because semiconductors with the band gap, okay, you have to apply some energy to the electrons. So the electrons are not okay. Thermal fluctuations are minimal. Never, it is there in the semiconductor, but since the electrons are bound to the valence band, you have to apply some electric field so that the electrons are coming to the conduction band. Right? In that way, the thermal effects are minimized in a semiconductor. So that's why you are seeing, you are able to see the Hall voltage or Hall effect in semiconductors even at room temperatures. Okay, that's why in general they use semiconductors in the lab. Okay, but nevertheless you can measure at very low temperatures. You can measure Hall voltage or Hall effect for metals also. Okay, but you have to be very careful to differentiate to account for the thermal fluctuations. Okay, because as you know, all the electrons, even all the more free electrons are freely moving on the surface of the metals, right? That's what we have seen in root theory. So they, you cannot, when you do actually all the more do it at room temperature, the measurement, so you cannot differentiate thermal fluctuations from the actual effect of electric field or the magnetic field. That is the major reason. In the lab experiment, you generally use semiconductors. Okay.
Yes,
Is it
sir.
clear?
It's clear.
Is there any other questions?
No, no other question
Are
right
there
now.
any other? Okay. So, okay. So we were seeing why is this Hall effect useful? Okay. Even Hall was thinking, okay, he has said, okay, after a lot of trial and error measurements, his aim was to measure means what is the effect of a conductor in a magnetic field. Okay, that's what is his doctoral thesis is. What is the effect of conductor, good conductor of electricity when you keep them in a magnetic field, right? That's what is this one, and that's how he found out. Okay, there are at a perpendicular to the both applied electric field as magnetic field. There is a certain Hall voltage. Okay, but how to what is that? How to use this one? Okay, or what is this effect useful for? Okay, that's what even at that time people were started thinking. Okay, but because there was no proper theory exists at that time. Okay, they could not identify it. Okay, but nevertheless they tried it. Okay, so as you can see, the concentration of the charge carriers, right, carrier density, they could find, but actually why it is why and where it can be used, okay, or how to make it useful for any practical applications. Okay, so that is what they could not able to understand. Okay, and even later on, after 100 years only, we could be able to use it effectively in different applications. Okay, but until 100 years, people were thinking that where it can be used. Okay, yes, the physics wise, basic physics wise, yes, everything was good. Like you can actually see the effect of Lorentz force on charge carriers, right? And the effect of electric field as well as the effect of magnetic field. You can actually see clearly in the experiment. But how to use them for practical application, that was the key. Okay, so but at that time, since even in 1879 there was no low temperature measurements, as you can see, only in 1910. Okay, Kamerlingh owns liquefied helium, right? He could go to 4 Kelvin. That was in 1910, right? But this was Hall effect was done in 1879. Okay, so they could not even think of low temperature measurements. Okay, since there was no concept of low temperatures at that, or how to go to low temperatures. Okay, they didn't even think of that. Okay, but the actual key was there in the low temperature measurement. So once after Kamerlingh once started, only the low temperature physics started, right? After 1910 only, right? So, but this was Hall effect was in 1879. Okay, almost 30 years before low temperature was even discovered. Okay, so that's where the key part comes in. Okay, this slide tells you that okay, low temperature and the sample has to be 2-dimensional. Okay, that's why the thickness of the sample doesn't matter. Okay, because only the surface charges were involved in the process of Hall voltage. Okay, so whatever you do, whatever thick sample you use, it doesn't matter. Okay, and another important point from here is that disorder also. Okay, on the surface, whatever disorder was there, it was not affecting the Hall voltage measurement. Okay, even if appreciable amount of disorder was there, and like some kind of scratch. That's why even you can roughly handle the lab, the students roughly handle the sample, right? The Hall effect measurement, whatever semiconductor sample, very roughly handled by the student. But nevertheless, you will not see any change, any appreciable change in the Hall voltage measurement. So n number of students handle it in a very rough way, the samples as well as the experimental setup. But nevertheless, you get the Hall voltage measurement all the time, okay, in a within error limit, right? You will get it. So it simply shows that, okay, the thickness of the sample doesn't matter, okay, as well as disorder, okay. There, as long as there are small amount of disorder, it doesn't matter. You will anyway you will get within the error limit the Hall voltage, right? So these are the, and okay, that's how semiconductor physics started, like these different silicon technology or different transistors. When they started using, they find out that for this Hall effect measurement, even small amount of disorder doesn't affect the Hall effect measurements, okay. So that, again, that's so in any experiment, any semiconductor experiment, okay, disorder plays a key role, right? Even if doping, right, N-type doping or P-type doping, you will talk about, right? So that appreciably changes the semiconductor properties, right? But in a given semiconductor sample, even if there are some amount of disorder, the Hall voltage doesn't change, okay? So that is what, that is again, so how the electrons behave in a given sample, not disorder. So the effect of disorder is almost negligible in Hall effect, okay? So that is another interesting phenomena which, see, any other property of a semiconductor, right? It's affected by the impurity, right? Or defects in the sample, right? If you have even if you have a small amount of disorder, right, you will get like your even simple IV characteristic, right, will be drastically changing for your, as you can see, for simple N-type or P-type semiconductors, right? But whereas the Hall voltage does not change, okay, appreciably, right, within for until for certain amount of disorder, okay. So that is what is the key. That is what people could not understand for quite some time. Even after the low temperature physics was invented, they say even with the disorder, it's not changing. The Hall voltage measurement is the same, okay, until even very low temperatures they didn't go, but to appreciate like liquid nitrogen temperature, right, or even liquid helium temperature, right, they could not see any appreciable change. But so that's where this two-dimensional Hall effect, okay. So they want to actually see whether the dimension of the effect, dimension effect is there in the Hall voltage or Hall effect measurements, right? So even they have started doing it after this silicon transistor technology comes into effect. They actually look into the effect of thickness, like you have a flat sample, like square or a rectangular flat sample, and measure the Hall voltage, okay. So surface current density and Hall voltage, like can you see the number or charge carriers in 2 dimensions, whether are they changing or are they not changing. So ultimately what they found is it does not depend on the shape of the sample, okay. So as you can see, 2 dimension, they have taken a completely, they have measured a pure 2-dimensional material, right, and measured Hall voltage and found that actually it does not measure, it does not depend on the shape of the sample, right. So that's what somebody has asked a question: cylindrical samples, whether can it be used, right? So yes, cylindrical samples can be used, but only thing is, first thing is you have to know the perpendicular direction of both the electric field as well as applied field as well as the Hall voltage. For measuring the Hall voltage, you have to accurately measure in a perpendicular direction, right? But so even if you measure, it does not going to change, okay? Whether it is a cylindrical sample or a square sample or a rectangular sample. That's what this pure two-dimensional Hall effect measurement shows that, okay? So again, this, so this is a very intriguing information. Like even if you put some small amount of disorder, it's not changing the Hall voltage, okay? Even in the sample, if there are some that you can see in your lab, right? Any solid state physics lab, any university or any college, right? The sample is used by n number of students, the same sample, right? Same apparatus is used. But so whatever way you use, your Hall voltage is not going to change as long as your measuring instruments are working fine, right? So you will not see any change in the Hall voltage measurements, right? So that is what is was bustling for all the time. It took almost more than 100 years, okay, to understand what why it is happening and how it is happening, how to understand what is the theory behind that, okay. See, experiment was done. So as you can see, Hall effect was done in 1879, right? But the actual proper theory, theoretical knowledge of Hall voltage or Hall effect was not known, okay? Even after 100 years of this experiment, okay? So experiment was devised long by 100 years, right? But there was no proper theory for the Hall effect, okay? So that is even after the invent of quantum mechanics or low temperature measurements, people could not give a proper theory for the Hall effect, okay? Until the integral quantum Hall effect comes into picture, right? Which is more than 100 years later than this Hall effect, okay? So these are, okay, some mathematical calculations, okay? It's, as you can see, the current density in different directions and the electric field resistivity measurements and the conductivity measurements in different directions, right? In a perfect two-dimensional sample, okay? Again, they see there is no, it does not depends on the dimension of the sample, right? Even with the simple simple analytical calculation as well as rigorous theoretical this one, they could not find any change in the Hall voltage, okay? So it was found out that the Hall voltage or Hall coefficient does not depend on the shape of the sample, right? So whether it's 2-dimension or 3-dimension, it's the same, because only the anyway the surface is participating. So 2-dimension doesn't matter here, right? So okay, so this is one of the okay, basic results of Hall measurements. Actually, this should be the way it should be done in the labs, in the any solid state physics lab, wherever this Hall effect measurement is there. Actually, you can measure the density and even mobility, okay, of the free electron gas, okay, in general, provided if you measure the electric field or the current density along different directions in a given sample during the actually Hall effect measurements, okay. So this one, if you do in the lab, so actually it gives you more information, which is like density of the number density of the charge carriers, and not only that, the mobility, which is the scattering time, the relaxation time, which we are talking about, right? In root theory, you can actually measure it, okay, or the mobility, right? The mobility of the charge carriers, okay, involved in the process. You can actually calculate by, okay, that's what is plotted as a function of magnetic field, right? So you can measure different directions, the resistivity or the current density, right, along x, y, or xx directions. Okay, so which in turn will give you the mobility mobile. So from mobility, you can actually calculate the relaxation time. Okay, which we have seen in root. The one of the most important parameters in root theory was like relaxation time. Okay, the time between two successive collisions, okay, of the charge carriers. So that you can actually directly calculate from these Hall effect measurements. So I think this is the way the Hall effect experiment should be done. Like instead of routinely measuring, okay, you apply electric field and magnetic field in perpendicular direction and just measure the Hall voltage. I think you should one should do this measurement like mobility measurements, like by measuring the current density along different directions, okay, and calculate the resistivity and using that to find the mobility of the charge carriers in the given sample, and using the mobility you should be able to find the relaxation time, right, or like scattering time of the electron gas. So that should be, so that will look like this as given in this graphs. Okay, so that should be the way for the Hall effect measurements in the. So it's not only about Hall voltage, but this mobility as well as carrier density as well as relaxation time. Okay, so you can. So I think we should. The students also should gain more insight into such kind of measurements, right? Instead of routinely measuring only Hall voltage, right? So we should concentrate more on this mobility and scattering time measurements, okay? So that, like suppose if we do it for different samples, different semiconductor or even metal samples, you should be able to tabulate, okay, for different sample, what are the mobilities and the relaxation times. So you can get a feel for how does the electrons, free electrons move in, okay, different metals or in semiconductors, okay. So you can have actually a feel for that, okay. So that's why this should be done, okay, as a function of magnetic field. If you do that, then you will get a graph like this one, right? So which will directly tell you the relaxation time or mobility of the charge carriers. Okay, so I think next time when you do the Hall effect measurements, I think you should try out this one. Okay, and okay, so this is again a summary of after 100 years. Okay, it is found that classically this is what is happening. Like thickness or dimension of the sample doesn't matter. So whether you take a thick sample or a thin sample, only the surface charges take part in the process, Hall effect process. Okay, and this is what as a function of magnetic field, the Hall voltage linearly changes. Okay, this is okay. These are all at room temperature or normal temperatures under ambient conditions. Okay. And people have not tried what happens in the low temperatures until even after 100 years. Okay, maybe they have tried at say liquid nitrogen or liquid helium, and nothing appreciable change is not happening, so they left it at that point. But okay, after 100 years, okay, then comes at some point, okay, and definitely after 100 years, okay, they tried at still further low temperature. Okay, at say this is at 1.2 Kelvin. Okay, when you, so this below whatever linear graph is given, this is at normal room temperatures. Okay, but the same thing if you do it in a, okay, the Hall boras do it in a very low temperature, like 1. Even less than liquid helium, right? Liquid helium is 4 Kelvin, right? But this is 4.2 Kelvin, right? As you can see, liquid helium, when Hamerling wants liquefied helium, right? It was 4.2 Kelvin, right? But this is 1.2 Kelvin, okay? So when you go to such low temperatures and apply very high magnetic fields, okay, the Hall voltage or Hall effect shows like steps, okay? Instead of a linear behavior, it shows in steps, and those steps are in definite numbers. So that's why it's called quantum or integer steps, okay? Definite numbers. So that's why it's called quantum Hall effect, okay? So that's okay. That happened well after more than 100 years of discovery of Hall effect, okay? Right from 1879 to I think around 1980, 85, okay? And I think 1985, this was done. When you do the sample at very low temperatures, you see a step-like feature happening, okay? Say for the same sample at room temperature, it shows a say linear behavior, but when you go to very low temperatures, okay, you see a step-like feature, so which is called as quantum Hall effect, okay? And these steps are in value of integer numbers, so they are called integer quantum Hall effect, okay? So the key this one of integer quantum Hall effect is that, okay, it happens at very low temperatures and very very high magnetic fields, which means that you almost froze the sample, right? Means you are almost free of thermal fluctuations, okay? So whatever the effect of magnetic field or temperature as well as magnetic field, you can clearly see that. So that's why it gives rise to different step-like behavior. So each energy level is filled once, okay, at a until particular field. Okay, that's what it shows. Like again, Bose-Einstein condensation. So this quantum Hall effect leads to many interesting phenomena like Bose-Einstein condensation as well as superconductivity, right? So that's where the real applications of Hall effect comes into picture. So which started people started undergoing and understanding it after 100 years, okay? So okay, this was done in 1985, okay? So 85 he got the Nobel Prize, okay? This is Professor von Kliching, okay? So he okay, I'm not going into the, because integer quantum Hall effect itself is again for a lecture topic, okay? But just I'm giving you a glimpse of that, okay? It's quantized in terms of integer, like each step has a different value, okay? But okay, this is what he has done. Why, how precise it is, okay? Why, what are the different values possible for each step, right? And again, another interesting observation is that even some small amount of impurity doesn't affect the measurement, even at low temperatures. Okay, so this is another interesting aspect. But the advantage of this integer quantum Hall effect is that it redefines the resistance value. Okay, the standard resistance value, right? You can measure the resistance better than in 1 part in 10 to the power 10. Okay, so this is what new definition of ohm. Okay? Resistance, that is what you get it from integer quantum Hall effect. Okay, and this was a very raw experimental setup of Professor von Kliching when he actually measured the measurement. Again, the story of this measurement itself is very interesting. Okay, he got it at one early morning, the result. Okay, that's what he wrote in his Nobel lecture also, right? So this is again very interesting to study how suddenly he find out what is integer quantum Hall effect, right? So you can also read about that. Okay. Those are available in Wikipedia and things like that. Okay. Okay, this is what, okay, basic summary of integer quantum Hall effect. Okay, he was awarded again Nobel Prize. Okay, very important, again, two-dimensional electron system. So it the step-like feature you can see only in two-dimensional systems. Okay, that's why they use two-dimensional samples. But okay, the Hall coefficient, Hall conductance is quantized in terms of the charge E square by H. Okay, or Hall resistance in terms of H by IE square. Okay, and this quantum of conductance is called glitching, right? A new standard parameter, right? Quantum of conductance is H by E square. Okay, so it is. But so once integer quantum Hall effect was identified, okay, there was no stopping. Okay, people started working on that immediately, and they found almost in different samples, right? You can find the different step-like features, right? And immediately after that, they started finding also there is something called until for some time they find that the steps are having integer values. Okay, integer number of electrons are filled in each step. But after immediately after this discovery, within I think 2-3 years of that discovery, integer quantum Hall effect, there is something called fractional quantum Hall effect. Okay, I'm not going into the details of that now, but there is something called you understand. Okay, you keep it that in mind. There is something called fractional quantum Hall effect. Okay, for the discovery of new form of quantum fluid. Okay, and actually this is what gives rise to again the realization of bosons in condensations and superconductivity in new systems. Okay, which were not known before previously. Okay, so this is the okay. These three scientists, Robert Loughlin and Daniel Choi and Stromer, were awarded this one. And so after this integer and fractional quantum Hall effects, we have a complete theory and experimental definitions of okay the basic Hall effect measurement. Okay, as well as even we have the theory of integer quantum Hall effect as well as fractional quantum Hall effects. Okay, and even in fact fractional quantum Hall effect was immediately awarded the Nobel Prize. Okay, within its discovery of 2-3 years, it was awarded the Nobel Prize. Whereas Hall, which who was discovered it in 1879, okay, he's beyond that Nobel Prize, so he didn't get Nobel Prize. Okay, but when we started understanding more after 100 years, okay, okay, this was a simple, okay, very raw experimental setup. Okay, at that time, 1990s, okay, early 1990s, how this quantum Hall effect, fractional quantum Hall effect was discovered. Okay, so that's what is written here. Again, there are this Nobel lecture you can visit. You can see in the Nobel Prize site. It's a very interesting account of how they discovered. Okay, fractional quantum Hall effects. Okay, they were trying for so much, but suddenly one point of time they got it. Okay, so they were so excited at that point. Okay, so this is how after 100 years, okay, the Hall effect gets its due in by way of integer and fractional quantum Hall effects. Okay, so I think okay, this is all I have prepared for this Hall effect. Okay, I thought of starting. So, is there any other queries you can ask me? Is there any other questions?
No, sir. No questions till now. Yes, attendees, if you want to ask something, you can post your questions in the chat box.
Yeah. Okay, that's the one thing again I want to emphasize is this one. Okay, the mobility and the uh, relaxation time or scattering time, you can call,
There is
right?
one question from Arya. She's asking that, sir, that means discovery of quarks was able using Hall effect?
What was discovery of?
Quarks. Quarks.
No, no. Okay, that what is written in the last line? No, no. It was in light water. He was okay. This was in his noble lecture also. But quarks means he. Okay, he explained. Okay, quarks. He got it like that. So okay, it's not actual quarks. Okay, that is different. This is what just jokingly he was saying. Okay, so that is this quarks is different. Okay, just a way of expressing things. Okay, that he got because they were thinking at the because at this time only integer quantum Hall effect was known. Okay, so when he was doing the actual experiment, okay, he was thinking that it should not come as integer, it should come okay, even fractional, other fractions also. Okay, means not only integer, it should come. So that's why he was exclaimed. Okay, he was very happy. So he said quarks, I got it. Okay. So it was not the actual quarks. Okay. So that's different. So, okay, what I want to emphasize here is this point, okay. This mobility and the relaxation time or scattering time, you can call it. Okay. These are the two key parameters which one a student should calculate while doing Hall effect measurement. Okay, instead of because now the Hall effect measurement is very routine one. Okay, but that will not give you much insight into the sample assets. Okay, but when you actually measure these quantities, mobility as well as relaxation time, so you will be okay. This is very informative both from the basic point of view, like BSc or MSc point of view, as well as from research point of view also, right? So in research point of view also, you can use this relaxation time or mobility can give you lot of insight to the nature of the material, given material, right? So in a Hall effect measurement, okay, these are the advantages. You can measure the mobility and the relaxation time directly. Okay, so I think the student should do this one as in the experiment. Okay, while doing the Hall effect measurement. Okay. Okay, the next. Okay, I didn't actually go into the details of. Okay, these are the basic root theory model where you can calculate the analytical model where you can calculate the different parameters like conductivity along different directions, right? Both in the parallel direction as well as in the perpendicular direction. So these are the basic calculations using again root theory, right? Simple root theory, classical calculations only. So these are available in any basic solid state physics book. Okay, so that's why I'm not going, but only I want you to note that okay, the parallel and perpendicular okay resistivity varies okay in the given sample. As you can see, the parallel resistivity or along the length of the sample is something like your what is that static DC electrical conductivity, right? And whereas the resistivity, right, along the perpendicular direction, okay, of the sample, right, which largely depends on the magnetic field, okay, because there is a Lorentz force acting on the charge carriers, okay. So these are the two parameters which okay, you should be able to calculate in the experiment also, okay, directly. But generally, okay, we don't do these measurements, but in principle, if you do this measurement, okay, it will give you information about to understand the nature of the given sample, right? Why, based on this information on resistivity, you can know, you can actually design the different means what are the inherent characteristic of a given sample, and okay, if you are doing research, how to improve the properties of the sample, right, based on this measurement. Suppose if you find something which you don't need or which you need, so the based on these measurements you can improve upon them, right? So that is so in a way it is a very basic measurement, but nevertheless it gives you a lot of insight into your sample, right? So that's why not like Hall effect setup should not be used only for measuring Hall voltage, okay? So that's what I'm trying to emphasize all the way, that it should be used in a much more it's a much more sensible way, okay, which by measuring all this resistivity or conductivity along different directions and corresponding mobility and scattering relaxation time, okay. So that will give you more information about the sample itself, okay. So okay, that's what okay, these are the things I want to emphasize. Again, you can see it okay, as I told this biography, I will show you one slide, okay, which I was reading. I will share it with you, okay. uh, just a minute, I will share it with you. This one. Are you seeing this one? Are you seeing this slide?
Yes, sir. Slides are visible. You are scrolling different slides.
Okay, so no one. Okay, I wanted to show you one thing, but okay, I think this is not that file. Or okay. Okay, since okay, there is some more time left. Okay, I thought I'll show you a very basic one. Okay, about not this one. Okay, just a minute, please. Or I will stop sharing and then I will open it again. Okay. I will stop sharing it. I will just open it 1 minute. Okay. Okay. Okay, still there is some time left. Okay, this is this is not a way I planned, but this is just a very general this one which I come across. Okay, this is not my slides. These are available in the web. Okay, just type it in Google, you will get it. Okay, so just I was looking for different things, so I just wanted to show you some of the. So when I was doing this in solid state physics, okay, what are the real what is it, discoveries made, or the Nobel Prizes in solid state physics, right? So that's what I came across, and I just wanted to share it with you. I think there are some 10 minutes left, right? I will just show you that, because if I start something new, it will not be over. So I will just use this 10 minutes for just, okay, to relax you, right? Okay, so this is just a story kind of thing. Okay, like the very first yearly discovery is Matheson's rule. Okay, this, you know, the uh, temperature as a function of resistance, right? That's what, this is what you use for superconductors, right? You use below this temperature, the superconductivity means it drops, the resistivity goes to zero abruptly, right? So that is what is Matheson's rule. That's what one of the early discoveries. Okay, the resistivity of a metal, okay, how it changes as a function of temperature, okay, which is as early as 1864, right? It was done. Okay, so this was one of the very early discoveries of in physics, or solid state physics in general. Okay, and okay, this was the original paper by Matheson. Okay, he has actually painfully tabulated all the values. Okay, so this is a cartoon showing okay, how at that time the people were looking at him for his painful job. Okay, one of the early discoveries. Okay, and the next one is about our next important discovery is about this one, Wiedemann-Franz law, okay, which is the ratio of thermal conductivity to the electrical conductivity. This I will plan in the one of the last lectures. Okay, so this is about Wiedemann-Franz law. Okay, the ratio of electrical and thermal conductivity. Okay, this again for different metals, he has tabulated it. Okay, for different temperatures as well as different this one. And okay, another important discovery is Hall effect. Okay, this is famous Hall picture of one of the rare pictures of Hall, right? 1879. Okay, this was his PhD doctoral thesis work. Okay, so this is what his actual experimental setup. Okay, along the thickness of the sample, you measure the Hall voltage. Okay, so okay, and again our Drew model, famous Drew model. Okay, this is what we have seen from 2-3 classes, and okay, the summary of Drew model. So the model also explains this Hall constant. Okay, but nevertheless, it could not explain why the Hall voltage increases linearly with magnetic field. Okay, so rest of the thing, even though it partially explains Hall effect, it could not fully explain. Okay, so that again, as a classical theory, it whatever it can explain, maximum possible, it does explain. Okay, so that's why even is worth doing now also. Okay, okay, these are the assumptions of Doom model, which we have seen. It uses Maxwell-Boltzmann. You have seen in like statistical mechanics, right? Maxwell-Boltzmann issue. But whereas when you say electrons, it has to be Fermi-Dirac statistics, right? That's what later on quantum theory of metals talks about Fermi-Dirac statistics, right? and it uses simple Newton's second law, right? So these are the things we have seen before, right? So just a summary of that. And okay, the prediction of Doom model greatest prediction, two prediction is this DC conductivity or Ohm's law in a generic manner, like J equal to sigma E, right? That is the that is discovered, that is prediction is based on Doom model. Okay, so that is a these are the two major predictions of Doom model. Okay, one is DC conductivity, writing Ohm's law in a generic way, and Hall constant means type of charge carriers from Hall effect measurements. Okay, so these are the two major predictions of Doom model. And again, okay, how it varies. Okay, somebody asked with metals and insulators, what happens? Okay, so this is the key for how it varies with the metals and insulators. Okay. So again, based on root theory, okay, and okay, this Sommerfeld theory is the one. It is called quantum theory of metal. Okay, he proposed once the invention of after the invention of quantum mechanics. Okay, he modified the root theory into quantum mechanics by putting Fermi-Dirac statistics. Okay, instead of Maxwell-Boltzmann statistics, he used Fermi-Dirac because electrons obey Fermi-Dirac statistics, right? So that's what he has done, and he has modified the root theory of metals. And okay, he's the famous Felix Bloch, okay, for quantum theory of electron dynamics, right? So he only proposed that in quantum theory, okay, not only electronic effects, but also ionic effects should be taken into account for metals to explain the theory of metal, right? And in the periodic potential of the given metals, right? So that is what this Felix Bloch's theorem, right? You remember the Bloch's theorem, okay? And okay, again, Schrodinger's theory for different particle in a box, right? And different medium periodic potentials, right? So that is what. And another major discovery in the 20th century is this one, Bravo lattices, crystal systems, right? Bravais lattices in 3 dimensions, 7 crystal systems, and 14 types of unit cells, right? All these things you can. So this is another one of the major. Okay, again he has discovered it in 1850. Okay, so and again this one lattice dynamics. Okay, so this is just a summary. I'm not going into the details of that one. So just to make you understand, okay, how gradually the solid state physics has improved over a period of time, right? Right from the beginning, right from 1850s or something, right? So lattice dynamics again, Einstein contributed like specific heat, Debye theory of specific heat, right? Einstein's theory of specific heat you all came across, right? So the Dulong and classical theory of Dulong and Petit's law of specific heat, right? So the lattice dynamics started in the early 1900s and things like that, okay? And then came like black body radiation, Planck's radiation and things like that, right? And then X-ray scattering, right? Von Laue or Bragg, right? Bragg's law, all the things came in 20th century. And okay, this is a famous low temperature, Hamelin Wons, right? He has discovered low temperature, like liquefied helium in 1909 or 1910. And then because of that, the superconductivity was discovered, right? So this you can now huge applications based on levitation, right? And this is what Meissner effect, right? Perfect diamagnetism by superconductors. superconductors, right? That is what is a Meissner effect. Okay, they expel the magnetic field. The perfect superconductor expel the magnetic field, or they are perfect biomagnets, right? That's what the Meissner effect shows, right? And okay, again, superfluidity, right? Many people work on superfluidity, like mostly Russians, like Lando, Kabitsa, and Bogalibov, and Feynman. Okay, they worked on different Bose, ancient condensation, and things like that, right? So these are another one of the major discoveries in solid state physics. Okay, and okay, these are the two people theory of superconductors, right? Superconductivity, Cooper pairs, right? So that's what is Cooper, Leon Cooper, and Frolix. Okay, so these are the two theory people invented the theory of superconductivity, and okay, of course, the famous BCS theory, right? But in Cooper, was discovered in 1957. Okay, and okay, these two are the high temperature superconductors, Muller and Bernoulli. Okay, and one of the from the electrical point of view, the major discovery is field effect transistors, right? By Bardeen and Shockley. Okay. So this Bardeen is the same one who discovered BCS theory, right? So he got 2 Nobel Prizes, right? That's what you know, right? One for the transistor and another for the superconductor, right? So, and again, our integer quantum Hall effect, right? So, which redefines the definition of resistance or ohm. Okay, what is ohms, right? And there is a new constant in the name of von Clichy, right? Von Clichy constant. Okay, and okay, these are the 3 people who are responsible for fractional quantum Hall effects. Okay, Laughlin proposed the theory, and Stromer and Tanshui, okay, predicted there are a fractional each plateau has elementary excitation with a fractional electric charge. Okay, and last but not least, the 2010 this one Nobel Prize is for graphene, right? Which is nowadays people are working in graphene-based materials, right? But Andre came measured that, and okay, this carbon nanotubes and quantum wires. Okay, these are the again. Okay, these are the currently ongoing research topics in solid state physics. Okay, so okay, so this is just I want to share with you. I think I'm done for today. Is it okay, or should I continue?
Yes, sir, it is
I think I'm
fine.
done for.
Yeah. So there is one question.
Yes,
Yeah,
yes.
yeah.
If there are any.
Are there any questions, students?
There is one question. Sommerfield model set positive Hall constant for some metals. What does it signify?
Uh, okay, okay. I didn't. Okay, I mean, I'm planning one of my lectures in Friday or Saturday on Summerfield. Okay, maybe at that time I will touch upon that. Today, okay, I didn't do still now Summerfield this one, right? So maybe in one of my lectures I will take it up. Okay, on Friday or Saturday something. Okay, is it okay?
Okay, sir. Yes, sir.
Yes, sir. Yes, sir. Students, if there are any other questions, please you can write them in the chat box. Dr. Senthil, everything was so clear. There are no questions.
Okay. Everything is clear. Okay.
So the students say, thank you, sir, for giving a brief summary of the growth of solid state physics. Yeah. I mean, you cannot connect to a subject by just, what is the formula of the subject? What is the definition of a subject and so on? You cannot really connect like that, And for example, once at this point, I'm reminded of a wonderful movie in which so the life of Faraday was shown as a proper movie. So
Yes.
real human beings acting as Faraday, and the intensity of his life and how devoted he was towards learning something, although he was working in a as a factory apprenticeship. So whole day he
Yes.
had to work in a factory, and after that he only in the night when his working hours were over, he used to listen to the lectures of one very famous scientist. I'm not remembering which one.
Yes. Yes. Yes.
And at that time scientists were supposed to hold public lectures. So they used to go to town hall and hold public lectures, and he used to note down
Mm.
everything there in a public lecture. And without any training, he decided to experiment, and that's how we have wonderful Faraday's laws of electricity. Today we can't even think of
Yes.
such thing that somebody will do such a thing. So sometimes getting connecting to the stories of the physicists who labored so hard to understand physics without any, without any examination on head, without any formulae to write and so on. And when ultimately he wrote down all his
Yes.
notes of his mentor and presented it to him, he was astonished. And he was astonished that how could anybody without any formal training, get inspired only by listening to town hall lectures given to a normal
Yes.
public and so on. So history of science is very important, and that is why now the government is making special efforts to introduce history of science to the undergraduate, postgraduate, and especially school children. It has started at the
Yes.
school
Yes.
level now, that you must
Yes.
know what was done in your own country and around the world in as far as the history of science is concerned. So I think it's very important aspect,
Yes.
and such stories are very inspiring that they could do so much just like that.
Yes.
So thank you so much for this,
Thank you.
and we'll have again a lecture with you soon. And so I think if there are any pending questions, they can be taken up in your next session.
Yes.
And so thank you so much, sir. Everybody is saying thank you to you. And I'll just take 1 minute to connect to the
Thank you.
next speaker. Yeah, yeah.
Yeah. Sure. Sure. So thank you, Punita. I have to leave now. Okay.
We'll give a minute break to the students. No problem, sir. Yes, sir.
Yeah.
Please. Thank you
Thank
so
you.
much.
Thank you. Thank you.
Yeah, so the next speaker has already joined, Professor Anirban from Calcutta University. Welcome, sir.